Welcome to Little English Studio, the channel where mathematics, science, and human curiosity come alive in clear and beautiful English. Today we journey into the elegant world of theoretical physics and mathematics to explore the Neother Theorem, a profound principle that links symmetry and conservation, a theorem that has shaped our understanding of the natural universe from the motion of planets to the behavior of particles. Join me as we follow the story of how abstract thinking became a tool to uncover hidden laws, tracing the brilliance of Emmy Neother, her insight into symmetry, and the countless ways her theorem illuminates the invisible threads that govern reality. The Neother Theorem, first formulated by the pioneering mathematician Emmy Neother in the early 20th century, is more than a mathematical statement. It is a bridge between symmetry and the conservation laws that underpin physics. The theorem asserts that every differentiable symmetry of the action of a physical system corresponds to a conservation law. This principle is deceptively simple in formulation, yet profound in its consequences. Symmetry, in this context, refers to invariance under continuous transformation. For example, if a system behaves the same whether it is translated in space, rotated, or evolved in time. Neother's insight was to formalize how these invariances guarantee the existence of conserved quantities. Consider the motion of a planet around the Sun. The laws of physics are invariant under time translation, meaning the same rules apply today as yesterday, from Neother's theorem. This invariance implies the conservation of energy. Likewise, invariance under spatial translation corresponds to conservation of linear momentum. Invariance under rotation leads to conservation of angular momentum. These are not coincidences. They are manifestations of underlying symmetry. The theorem applies broadly across classical mechanics, field theory, quantum mechanics, and relativity. It is a unifying principle, a key that unlocks hidden order in the cosmos. The story of its discovery intertwines with the life of Emmy Neother, a German mathematician working at a time when opportunities for women in science were limited. She studied under luminaries like David Hilbert and Felix Klein. Absorbing the language of variational calculus and the formalism of Lagrangian mechanics, the challenge was to connect abstract symmetry transformations to concrete, measurable quantities. Neother realized that by examining the action integral, a central object in Lagrangian mechanics that encodes the dynamics of a system, one could systematically derive conservation laws from symmetry principles. This approach transformed theoretical physics, providing a methodical pathway to identify conserved quantities without relying solely on experimental observation. Consider an electromagnetic field. The invariance under phase transformations of the field leads to the conservation of electric charge. In particle physics, internal symmetries described by group theory predict conservation laws that govern the behavior of fundamental particles. Neother's theorem provides the scaffolding for modern gauge theories, including quantum electrodynamics and the Standard Model. The applications extend beyond physics. In cosmology, the invariance of spacetime symmetries helps explain the large-scale structure of the universe and the constancy of physical laws over time. Engineers and applied mathematicians use symmetry principles derived from Neother's insight to simplify complex mechanical systems, reducing computational complexity and revealing optimal design principles. The elegance of the theorem lies in its generality. It does not prescribe the laws themselves, but rather identifies the consequences of their symmetries. This means that discovering a new symmetry immediately reveals a conserved quantity, a powerful tool in both theoretical exploration and experimental prediction. For example, in fluid dynamics, the invariance under translations and rotations leads to conserved momentum and vorticity constraints. In quantum mechanics, symmetries dictate allowed energy levels, selection rules, and particle interactions. The mathematical formulation involves defining a Lagrangian function that captures the kinetic and potential energies of a system, identifying continuous transformation groups under which the action remains invariant, and deriving the corresponding conserved currents or quantities. While this may appear abstract, it has direct, tangible consequences. From calculating the trajectories of spacecraft to predicting the decay of subatomic particles, the theorem bridges the visible and the invisible, connecting geometry, algebra, and physical observation. Historically, Neother's paper faced initial resistance, published in 1918 amidst the upheaval of post-World War I Germany. Its significance was not immediately appreciated, yet over the following decades, physicists recognized the deep insight it offered. Albert Einstein himself praised its elegance and utility. The theorem exemplifies the synergy between mathematical abstraction and empirical science. It transforms questions of what is conserved into questions of what is symmetric. Thus reframing problem-solving across disciplines, modern research continues to explore extensions and applications. Generalized symmetries, discrete symmetries, and broken symmetries expand the reach of Neother's original insight. In condensed matter physics, symmetry breaking explains phenomena such as superconductivity and magnetism. In cosmology, symmetry considerations underpin inflation models and conservation of energy momentum in curved spacetime. Pedagogy has embraced the theorem as a cornerstone of theoretical physics education. Students learning classical mechanics, quantum field theory, or relativity encounter Neother's theorem early as a fundamental principle that links diverse topics. It exemplifies the beauty of mathematics as a lens to understand the natural world. Beyond technical applications, the theorem inspires philosophical reflection. It suggests that the laws of nature are organized around symmetry, that the universe has a deep coherence, that patterns in motion, force, and interaction are reflections of abstract principles that transcend immediate observation. This insight echoes in art, architecture, and the human perception of harmony. Symmetry as a guiding principle appears in music, design, and visual composition. In this sense, Neother's theorem is not only a scientific achievement, but a celebration of the interplay between human intellect and the underlying order of reality. To witness the impact of Neother's work, one need only look at modern physics. Every calculation of conserved momentum in a particle collider, every derivation of angular momentum in astrophysics, every exploration of gauge invariance, every analysis of a dynamic mechanical system carries her legacy. The theorem exemplifies how an idea, abstract and elegant, can illuminate the workings of the universe, guide practical experiments, and provide a unifying framework that connects seemingly disparate phenomena. Her insight reminds us that mathematics is not merely a tool, but a language through which we decode nature, that symmetry is not merely aesthetic but operational, that conservation is not merely observation but a consequence of deeper principles. Neother's theorem continues to inspire researchers, guiding investigations into complex systems, inspiring new models, and revealing the subtle architecture of the natural world. It demonstrates the power of pure thought, careful reasoning, and courage in confronting the unknown. The story of Neother's theorem is both a scientific triumph and a human story, of a brilliant mind challenging conventions, advancing understanding, and leaving a legacy that touches every corner of physics, mathematics, and beyond. It is a reminder that the universe is intelligible, that patterns persist, and that insight can transform our relationship with reality. In classrooms, laboratories, and research institutions, students and scientists explore the consequences of symmetry, uncover conservation laws, and discover new phenomena. Each application, whether predicting particle interactions or modeling mechanical systems, is a testament to the enduring power of Neother's insight. From the small scale of subatomic particles to the vast expanse of cosmological structures, the principle resonates, revealing that conservation and symmetry are inseparable, that every invariance carries meaning, and that the language of mathematics and physics is a universal tool for understanding the world. By following the threads of symmetry, we see the universe as a coherent tapestry, each law, each interaction, each conserved quantity a stitch in the vast, elegant fabric. Emmy Neother's theorem is a beacon that illuminates the hidden order, a bridge between the abstract and the tangible, the theoretical and the empirical, reminding us that through careful thought, observation, and reasoning, humans can glimpse the profound harmony underlying existence. And that was our journey into the profound beauty of the Neother theorem, a window into how symmetry gives rise to conservation, and how abstract mathematics reveals the hidden structure of our universe. If you enjoyed this exploration of science, mathematics, and the elegance of theoretical insight, please like this video. Leave a comment telling us which symmetry or conservation law amazed you most. And subscribe to Little English Studio for more cinematic stories told in clear and beautiful English. Until next time, stay curious, keep exploring, and remember that the universe often speaks in the language of symmetry, and every pattern has a story to tell.